Okay, in lesson 8.3, we're going to extend our understanding of similarity to actually prove that triangles are similar. If you're looking below at the boxes, you think, oh, it looks pretty similar to congruence, and in some ways it is. Our learning targets are I can state the theorems to prove the two triangles are similar, so you need to know what the three of them are, and then obviously I can use them in proofs to prove similar triangles. All right, so angle-angle similarity, you can abbreviate like this, AA similarity. And it says if two angles in one triangle are congruent to two angles in another triangle, then the triangles are similar. So if I had A, B, C, and D, E, F, if I had angle A congruent to angle D and angle B congruent to angle E, then I would say triangle ABC is similar to triangle DEF. This is far and away the most popular one that we will use. Angle-angle similarity is the one that comes up most often because we have a lot of information about congruent angles. Side angle side similarity, we can abbreviate like this, SAS with the squiggle. Let me show you as an example first, and then we'll write it up. Let's go back to these same two triangles. So obviously we have to have an angle. So let's say we have angle A and angle D, but now we know from our definition of similarity that sides in similar triangles are not congruent, but they're proportional. We also know from our work with congruent triangles that SAS means the angle has to be between the sides. So we want sides to be proportional, and we're talking about the sides surrounding the angle. So if this is my angle, the one side is AB. AB would have to correspond to DE. And on the other side of the angle is AC, and that would have to correspond to DF. So notice the sides here have nothing to do with the congruence, but the ratio of the sides surrounding the angles, right, must be proportional. All right, so if I'm going to say that here, I'm going to say if an angle in one triangle is congruent to an angle in another triangle, and the sides surrounding those angles are proportional, then the triangles are similar. I think you can see why this one's a little bit tougher to use because we don't often have information about proportional sides. And you'll see an example or two of how we use this. So here, side, side, side similarity, right? You can now guess on how this one might work. This is all about the sides, so I need all three sides proportional. I'd have to have AB is to DE, as AC is to DF, as BC is to EF. I would have to have all of those proportional. So if the sides of one triangle are proportional to the sides of another triangle, then the triangles are similar. Okay? And that, of course, would be SSS similarity. All right, so let's do some example proofs. Don't think you'll find this too different than what we've done before. It is going to bring in some old ideas. So, for example, here we have a parallelogram as given. Let's kind of highlight that to see what it is here. That's ABCD. That's that guy is the parallelogram. And I'm trying to prove that these two triangles are similar. Well, again, you always want to lead towards angle-angle unless there's some obvious information about proportional sides. So I'm thinking about angles and I see parallelogram. I know parallel lines give me angles. So I think the first thing I'm going to do is say that these opposite sides here are parallel. DC is parallel to AB. If I have a parallelogram, then opposite sides are parallel. I know those parallel lines get me angles, so for example, right here I see a Z. Those are alternate interior angles, so I can say angle C is congruent to angle FBE. If parallel, then alternate interior angles congruent. But I see another Z, it's kind of a backwards Z. If I go here, that gets me those two angles congruent. That would be the same reason, so I could say angle E is congruent to angle CDF. Those are also alternate interiors, but now I have two angles in one triangle that match two angles in another triangle. That is enough by the above to say that they are similar. So triangle BFE is similar to triangle CFD by angle-angle similarities. So in some ways it's going to be a little quicker than congruence because you're looking for less pieces. Let's try a few more. Okay. This is a little bit of an unusual one, so stick with me here. We have LP perpendicular to EA. We have N is a midpoint of LP, and we have P and R trisect EA. All right, so let's start with the perpendicular because that's easy. I can say what these are right angles right there, so angle NPE and angle NPA are right angles. If perpendicular, then right angles. I can get them congruent. NPE congruent to NPA. If right angles, then congruent. All right, the tricky part about this one is this midpoint and trisect information is actually information enough for you to show some proportional sides. And I think the easiest thing to do would be kind of to mark it up. All right, so let's start with midpoint here. This guy, if N is the midpoint, that means those two segments are congruent there in the green. And if P and R trisect EA, that means these segments in orange are congruent. So we're not going to write it that way because we want to write it as a proportion. So if I'm looking at the little triangle and I'm looking at the big triangle, focus on the green. What's the ratio of NP to LP, right? NP is one of these green segments. LP is two of these green segments. So could I say that NP is 1/2 of LP, right? NP is half of LP. NP is one green, LP is two, right? And I'm going to do that saying the midpoint. If midpoint, I'm going to still say two congruent segs. I'm just not writing them as congruent segs. I'm writing that information as a ratio instead. Now look at the orange, right? I want to talk about this side of the triangle versus this side of the triangle. Just like in the greens, this guy's made up of 1, this guy's made up of 2. So can't I say EP equals 1/2 of PA? That comes from the trisect. I'm just writing it in a very different way. If trisect, then 3 congruent segments. I'm just choosing to write it as a ratio. So again, this little side of the triangle, this green one, on this little triangle, this green is 1 marker. In this side of the triangle, this side right here has 2 green markers. That got me NP half of LP. And then 1 to 2 here makes this half of this segment. Now those ratios match, right? So look at, I have an angle, and on each side of that angle I have an orange and a green, and on this side I have an orange and a green. So then those triangles are similar. Triangle pen similar to triangle pal by side angle side similarity. So I think you can see based on that one why we don't use this very often, because it's pretty tough to get those ratios. All right, here is a diagram that you're going to see a lot. KH is an altitude to GJ, and we have right triangle GHJ. All right, so altitude I know gets me right angles. I have a right triangle, but I don't know what I want yet. So let's look at these triangles. KHJ is this green one right here. And then HGJ is that big yellow one. I'm trying to show that those are similar. All right, so where are the right angles that come from here, right? KH is an altitude. I believe this is the right angle I want because it's in the green one. So angle HKJ is a right angle. If altitude, then it makes right angles. And then I have a right triangle. That's this big yellow one. So this must be the right angle that I want in the yellow one. So angle JHG is a right angle. And I'm just going to say if I have a right triangle, then it has a right angle. That's kind of trivial. Now I can get them congruent. HKJ congruent to JHG. If right angles, then congruent. But I'm kind of stuck because that's only one angle. I have one angle in the yellow and one angle in the green. Well, I highlighted them so that you could see something key, right? Don't they share an angle? If you're not seeing it, look at the top, right? Right up here, angle J is in both the green and the yellow. So I can say angle J congruent to angle J by reflexive. Now I have two angles in the green and I have two angles in the yellow. So triangle KHJ similar to triangle HGJ by angle similarity. All right, down below here it says the sides of one triangle are 8, 14, and 12. The sides of another are 18, 21, and 12. Show the triangles are similar. So here's what students tend to do. They say, okay, 8 is to 18. That's what 4 is to 9. And then they say, oh, 14 is to 21. 7 goes in there twice. 7 goes in there 3 times. And then they start to get concerned because then they say 12 is to 12. That's 1. And none of those ratios are the same. All right, so think for a minute. What did we do wrong? Why aren't those ratios matching up? Well, when they said the sides and these sides show they're similar, does it necessarily mean the 8 corresponds to the 18 and that the 14 corresponds to the 21? How do we decide which side corresponds to which side? My hint would be put them in order from lowest to highest, right? So this would be 8, 12, 14. This would be 12, 18, 21. Now I know the shortest side must go with the shortest side. That's 2/3. The middle side must go with the middle side. 6 goes in there twice, 6 goes in there 3 times. The longest side must go with the longest side. That's 2/3. Now they're all the same. So now you've showed by side similarity that those triangles would be congruent. Okay, so think about which sides you're matching up when you make your ratios. All right, we're going to try just these top two. I'll try to do these quickly here. These are not long proofs. DE parallel to AB. So those two are parallel, and I'm trying to get these triangles similar. So I'm trying to get this green one similar to this yellow one. Right? Hopefully you're looking at those parallel lines and you see those angles and you think about corresponding angles. Angle E congruent to angle CED. If parallel, then corresponding angles are congruent, but you should see another pair at the bottom of those triangles. So I can add angle B congruent to angle EDC by the same reason. But now I have two angles in the yellow matching two angles in the green. So triangle ABC is similar to triangle EDC by angle similarity. All right, on this one we have AB congruent to AC. Let's mark that AB and AC. I'll mark it like that. I have AD perpendicular to BC and EF perpendicular to AC, so I can get some right angles. All right, I'm going to look at the triangles I want here. ABD, where is that? ABD, that's that one. And ECF, which is that one. So I think I'm going after the perpendiculars first, because if AD is perpendicular to BC, I can get a right angle in that green triangle. ADB is a right angle. But then if I have EF perpendicular to AC, I can get a right angle in that yellow one. So I'm going to say that's also angle EFC. And that's if perpendicular, then form right angles. And now I can get those congruent. ADB congruent to EFC. If right angles, then congruent. All right, so I have one angle. So now I need another one. So you have to ask yourself, why did they give you this? Why did they give you AB congruent to AC? Well, isn't that an isosceles triangle right here? And if sides, then angles. So I can get angle, I really messed up my picture here, ABD congruent to angle ACD. If sides, then angles. But now I have two angles in the green and I have two angles in the yellow. So therefore triangle ABD is similar to triangle ECF by angle-angle similarity. Okay? And that's it for this lesson.